Hey there, in this video I'm going to try to give a brief introduction to what a weak heap is. I'll try to explain how it works and how it can be used to sort faster than quicksort. Before we begin, let's do a quick history lesson. About 30 years ago, the concept of a weak heap was pieced together by Ronald Dutton at the University of Central Florida. In his research article, he describes weak heaps as a data structure defined by relaxing the requirement for a heap. To start off, let's look at the rules that define how the data structure works. There's basically three rules that bring together the structure of a weak heap. First, the value in any node is at least the value of any node in its right subtree. The root has no left subtree. And finally, nodes having fewer than two children, except the root, appear at the bottom two levels of the tree. If you're anything like me, it's probably a little hard to visualize what a weak heap looks like, so let's bring in an actual representation of it and walk through these rules one by one. The first rule guarantees that a given node will always be greater than or equal to all of its right children. So in this case, the head node, which has a value of 20, is greater than all three of its children, so the 10, the 19, and the 9. However, notice here that the 10 has a child 19 that is greater than it. That's okay. This is a left child of the 10, and so we don't have to worry about it being less than the 10. The second rule keeps the root from having any left children, and the neat thing about that is if you combine it with rule 1, then we guarantee that the root has to have the largest value in the tree. The last rule essentially just guarantees that the tree ends up being well balanced. If we add some nodes to the tree, we can see one more interesting feature of a weak heap. Any node in its right subtree is a weak heap. Notice that the 10 node, without its left subtree, is a weak heap. Alright, well if you're familiar with what a heap is, you might be asking what makes a weak heap weak? Well, there's two main reasons. First, unlike regular heaps, weak heaps do not require that all of the bottommost nodes be as far left as possible. Additionally, the value in the left subtree of each node is totally unrelated to its parent. So weaker doesn't really mean that the structure is less capable. It actually means that the rules are less strict, which allows us to upkeep the heap without having to do as many operations. Before we can jump into how weak heaps make sorting faster, we need to consider a very important operation, merging. Merging two weak heaps together is done in a few steps. First, the root node containing the largest value becomes the root of the merged tree. The smaller tree with the smaller root becomes the right child of the root chosen in step 1, and the remaining right child of the tree with the larger root becomes the left subtree of the root of the tree in step 2. Now that's a bit confusing without a visual, so let's go ahead and look at an example, and I think it'll become a lot more clear. So now, the first thing we need to do is go ahead and choose the largest of the two roots. Here the two roots are 30 and 20, so we'll choose 30 and bring that to the middle. Then, we're going to take the whole entire right tree and make that the right subtree of 30. And finally, we can take the remaining portion of the left tree and go ahead and bring that over, making it the left child of the right tree's original root node, or the left child of 20. Now, if we go back, bring in the rules from before, and look over this tree to make sure that it still follows them, you'll notice that rule 1 holds. The values under 30 are all less than 30. So we're good there, and you can check each individual node too if you'd like. Also, the root has no left subtree because of how we merged it. And finally, you'll notice that the nodes 23, 9, 19, and 9 all have no children, so fewer than 2, and they're also on the bottom row. So rule 3 also holds. Alright, so merging is really important. But another thing that's really important is how we represent weak heaps in memory. We can do this with an array that is one element longer than the number of nodes we have in our weak heap. So if n is the number of nodes in our weak heap, Then here, n would be equal to 8, and our array would need to be of length n plus 1, which is 9. Then, once we have the array, we can place all of the nodes into the array in the same order that we would do a breadth-first search. And here's the values for the order we would reach the nodes doing a breadth-first search. Before we go ahead and put this into the array, I want to just point out one interesting thing here. If you look at the node 20, that would be element 1 in our array, and the left child of that would be 2 times 1, or 2, and the right child would be 2 times 1 plus 1, or 3. And you can see the rules on the right side of the screen here. You can always find the two children of a particular node by looking at double that node's index and double that node's index plus 1. Okay, now we can go ahead and move these nodes into their appropriate spaces in the array H. But there's one more detail about the array representation that is vital to the WeakHeap stellar performance. When we merge two WeakHeaps together, remember how we needed to swap branches around? Well, rather than moving left children to the right and right children to the left, we can simply have a second Boolean array called reverse. In reverse, we can indicate which node is the left and right child of a given node. If the value at the ith position in reverse is true, then double that has the right child. If false, then it has the left child. Since node 20, which is the first element in the array, had 15 as its left child and 10 as its right child, we would put a false at position 1 to indicate the element at position 2 of the array is its left child. Filling out the rest of the array looks like this. Alright, now that we know the array representation and how to merge, we can go ahead and look at how sorting works. The first step when sorting is always to take the head of the tree and move that to the last position in the array. Then we need to go ahead and break these two branches so that we can disassemble the tree and then merge it all back together. Now we can go ahead and merge the two smallest trees together, and that looks like this. And then we can go ahead and merge the two remaining trees together. So we'll select the bigger of the two heads, and then we'll move the other tree over, and then we can bring in the remaining part of the first tree, and now we have a WeakHeap again. And we'll just keep repeating this process over and over again until we've sorted all of the nodes. And now we're done. To wrap things up, let's go over some of the benefits of sorting with a WeakHeap. First, due to the use of reverse bits, we can simulate all of the branch swaps that are required when we're doing all of those merges really fast using that reverse array. Second, the relaxed rules keep us from having to bubble up every time as in a standard heap. And finally, the operation of sorting that we just looked at can all be done in place. That's why there was an extra position in the array earlier. Here we can see a comparison between WeakHeap sort and quicksort. You'll notice that it's kind of hard to tell, but WeakHeap sort is marginally faster than quicksort for the entire of the duration. If we zoom in more on this graph, you can see that a little clearer. And that's pretty much it. Thanks for watching this introduction to WeakHeaps, and I hope you found this information useful.